Yeah, and you can go ahead, Simon.
Okay, thank you. Today I want to talk about work that I've been doing over the last year, working on the role of minor species in crystallizing white dwarfs, and in particular how this relates to the ultramassive white dwarf cooling anomaly. So this is work I've been doing at Los Alamos National Lab in very close collaboration with Blouin Daligault and Didier Saumon, also at Los Alamos. So my plan for the next 20 minutes is first to explain what this ultramassive cooling anomaly is. Then from there, I will introduce the idea of neon 22 distillation and how it can explain this anomaly. I will then explain how this same process can also alter the evolution of more normal white dwarfs. And finally, I will say a word about the possibility of other distillation processes in crystallizing white dwarfs. So this story really starts with the core crystallization of white dwarfs. So the plasma in the interiors of white dwarfs is highly coupled because it's very dense. And as the white dwarf cools down, this plasma just becomes more and more correlated. And at some point, it's just so correlated that it decides to freeze into a lattice structure. So this is a liquid to solid phase transition that we refer to as the core crystallization of white dwarfs. And it's a very important event in the life of the white dwarf because this phase transition releases latent heat. And this latent heat is a new source of energy for the white dwarf. It's excess energy that it has to get rid of in order to continue cooling down, which means that it slows down its evolution, its cooling by a quite significant amount. On top of this latent heat release, you also have a phase separation or chemical fractionation process. So what happens here is that when, so I will take the example of a carbon-oxygen white dwarf. So when the carbon-oxygen mixture starts to freeze, the crystals that are formed will tend to be enriched in oxygen compared to the average oxygen abundance in the liquid mixture. And because the crystallization of the core starts at the very center of the white dwarf, where the density is at its highest, it means that this process of phase separation is gradually building a concentration gradient, where you have more oxygen at the center of the white dwarf and less oxygen in the outer layers. So by moving the oxygen ions around like this, you are, of course, releasing gravitational energy. So it's also a new source of energy for the white dwarf. It's excess energy that it has to get rid of. So it also slows down the cooling of the white dwarf by an amount that is of the same order of magnitude as that induced by latent heat release. So the signature of those two excess energies has been identified in the Gaia HR diagram. So here I'm taking a plot from Tremblay et al. 2019. So every little dot here is a white dwarfs. The white dwarfs, they evolve here to the right along the blue cooling tracks. And the interesting part is this thing here that has been called the Q branch, where you can see that there's an overdensity of objects compared to times before or after the Q branch. And this has been interpreted as being due to the crystallization of white dwarfs. So those two orange lines, they show where we expect the crystallization of the carbon-oxygen core to take place. So that's where we expect those white dwarfs to release this gravitational energy and latent heat. So they evolve more slowly when they are there. So that's why we see kind of a traffic jam of white dwarfs over here. A couple of months later, Cheng et al. Looked at this in more details, and especially they looked at the kinematics of those objects, which gives you another assessment of their age. And what they found is that for very massive white dwarfs, you cannot really explain the existence of the Q branch just with the extra delay induced by core crystallization. So it looks like there's another delay that is needed to explain the overdensity on the Q branch, and that's a delay that's currently not included in the white dwarf cooling models. So more specifically, Cheng et al. Concluded that you need 6% of ultramassive white dwarfs, so white dwarfs around 1.1, 1.2 solar mass, to experience an additional 8 gigayear cooling delay, right when they are in the process of crystallizing, so when they are in the Q batch. So of course, that's a big challenge to our understanding of white dwarf cooling. 8 gigayears is not a small thing. So the question is, well, what's happening? What's causing this extra delay? So very quickly, actually right toward the end of the Cheng et al. Paper, neon-22 was identified as the prime suspect. So because neon-22 has those 2 excess neutrons, in the sense that it has 2 more neutrons than protons, it can release a lot of gravitational energy if you find a way to move it from the outer layers of the core towards the very center of the core. In fact, if you move 1 gram of neon-22 from the outer layers towards the center of the white dwarf, you will release about 25 times more energy than if you move 1 gram of oxygen-16 from the outer layers to the center. So this means that even though neon-22 is only a trace species in the carbon-oxygen white dwarfs, so we're talking about something like 1 or 2% mass fraction, so even though there's very little neon-22, it has the potential to have a very strong impact on white dwarf cooling. So now, how do you move neon-22 from the outer layers to the center of the white dwarfs? The most commonly discussed mechanism to do that is simple gravitational settling. So neon-22 feels a net downward force in the white dwarf, so it wants to sink down. And that's what this little animation is showing here. So this is from calculations by Antoine Bédard in Montreal. And so you see the neon-22 sinking down, but this process stops at some point. And this is because this can only take place when the core is liquid. Once the core is solid, the neon-22 can no longer move. So this sets an upper boundary on how much neon-22 you can actually move to the center of the white dwarf. And because of that, we know that you cannot induce a delay of more than about 1 gigayear if you use a standard assumption for neon-22 gravitational settling. So there have been 2 proposals to boost this delay so that the neon-22 could perhaps explain the Q branch anomaly. So the first one by Bauer et al. Is to form neon-22 clusters in the core. And then the idea is that those clusters would sink faster than if the neon-22 were sinking alone by themselves. However, the problem with this proposal is that molecular dynamic simulations have later shown that those neon-22 clusters would not be stable in carbon-oxygen white dwarfs. So it looks like we need to rule out this scenario. A second idea is to simply boost the neon-22 abundance. So if you have more neon-22, you'll have more neon-22 gravitational settling. So Kamisasa et al. Using the La Plata code found that if you assume something like 6% neon-22, then you can produce a delay that has the right magnitude to explain the Q branch anomaly. But it's still very unclear how you can actually achieve a 6% neon-22 abundance. So this is much higher than what is predicted by standard stellar evolution. So that's a significant issue with this proposal. So we know that neon-22 has in theory all the gravitational potential energy that we need to explain the Q branch anomaly, but it looks like simple gravitational settling is just not enough to move this neon-22 and release this gravitational energy. So then the question is, well, is there perhaps another way to transport the neon-22 to the center of the white dwarfs? And we think we have identified such a mechanism. So over the last 2 years, we've worked on developing a new, very accurate technique to compute the phase diagrams of dense plasmas. So phase diagrams are the things that we need to quantify the chemical fractionation between the solid and liquid phase upon crystallization. So by how much does the composition of the solid changes when the crystals are formed during crystallization. So we use our new state-of-the-art technique to investigate the phase separation in a 3-component carbon-oxygen-neon mixtures. at a level of accuracy never reached before. And what we found, very interestingly, is that there is a large range in the parameter space where the solid crystals are impoverished in neon compared to the liquid phase. So that's what this plot is showing here. And if you have crystals that are poor in neon 22, then it also implies, under some conditions, that those crystals will be lighter than the liquid in which they form. So that's what the bottom plot is showing here. So you're forming crystals that are lighter than the liquid in which they form, which is really the opposite of what we have normally with simple carbon-oxygen phase separation. So normally you're enriched in oxygen, so the crystals are heavier and they just stay where they're formed. But here they are lighter. So what does this mean for the evolution of our white dwarf? So actually, this scenario, so that has been called neon 22 distillation, has been discussed already 30 years ago by Izard et al. 1991. So at the time, it was based on effective two-component phase diagrams. So here we've done the full calculations with all the physics and the three components, but really the idea of this process of neon 22 distillation was already out there in the early 19th. So what's happening is that the crystals that you form, it wants to float, right? Because it's lighter than the surrounding liquid. So it floats, and by floating up in the white dwarf, it will displace liquid that is, by definition, more enriched in neon 22, because this crystal is impoverished in neon 22. So of course, the liquid is by definition more rich in neon 22. So this crystal eventually melts someplace higher up in the white dwarf core. And this process just keeps going on. So floating crystals and displacing neon 22 rich liquid. So it keeps going on until you reach a very particular point in the phase diagram where we can predict that the mixture will just freeze at this constant composition. And this constant composition is 30% neon 22. So this is a way of forming so this means that this process is really efficient at transporting all the neon 22 in the core towards the very center of the white dwarf and form a very neon 22 rich core. So about 1/3 of this core would be composed of neon 22, and the rest of the core would be essentially containing no more neon 22. So that's exactly the kind of process we want to explain the Q-branch anomaly. Another key aspect of this process is that it is very selective. So that's what this plot is showing here. So let's say you have 60% oxygen in your core, so that's a standard value. Then what this plot is showing is that you need more than 2% neon for this process to kick off right when crystallization starts and form a neon 22 rich core. If you have less neon 22, so let's say you have a more standard 1.4% neon 22, then you're in this region where the crystals are heavier than the liquid, so distillation cannot take place, and the evolution will be different. So I will come back to this case a bit later, but for now, let's just keep in mind that a very crucial aspect of this process is that you really have a qualitatively different outcome depending on the exact composition of your core. And that's really something that we want, because we know that the Q-branch anomaly is there for only 6% of white dwarf. So we need a process that is really selective. So I think neon 22 distillation really is the solution to the ultramassive cooling anomaly because it ticks all the boxes. So first, we've computed that it has the right magnitude in terms of cooling delay, assuming a moderate neon 22 enrichment. So this can be explained by standard stellar evolution. Secondly, its effect is highly peaked on the Q branch because by definition, it happens right when the star starts to crystallize. So that's exactly what we want. And in the observation, it's very clear that this missing delay is happening over a narrow range of luminosities, which we are providing here. And it's not clear that simple gravitational settling can do the same. And finally, the third aspect, which I've just discussed, is that it's a very selective process. So we can add this new physics to cooling models without completely changing our understanding of the cooling of normal white dwarfs, which is a good thing because we know that our cooling models are not that bad for most white dwarfs. But there is more to this process, and I think it's actually very important also for our understanding of the cooling of more standard white dwarfs, so not just the ultramassive white dwarfs. So it turns out that normal white dwarfs also appear to experience a kind of cooling anomaly. So I think it's best illustrated by this plot here from Killick et al. 2020. So the top panel here shows the mass temperature distribution observed in the large sample analyzed in Killick et al. And the bottom panel shows an attempt to replicate this distribution using population synthesis simulation. And a difference that's very obvious between the two is that there is this overdensity here in the observations, which we just don't see in the simulations. This overabundance, so those two blue lines, they indicate where crystallization takes place. Okay, so when a star is between those two blue lines, it's in the process of crystallizing. So this overdensity that we see here is telling us that when about 50% of the core is crystallized, for some reason, those white dwarfs just start evolving more slowly until they are done crystallizing. And this is not explained by current cooling models. And you can also see this cooling anomaly in the white dwarf luminosity function. So this, again, is from Tremblay et al. 2019. So there is this peak here that is not reproduced by the models. And it's really, it happens at the same luminosities as this overdensity that we see here. So my hypothesis is that neon 22 distillation can also explain the second delay. So what will happen with those stars? So assuming they have a standard composition, so 60% oxygen, 1.4% neon. At first, they crystallize just as normal, so there is no distillation, just plain old carbon-oxygen phase separation. But as this phase separation takes place and as the crystallization front moves outward, you have less and less oxygen in the layers that you're crystallizing. And at some point, you have so little oxygen that you actually cross this boundary here between the no distillation and distillation regime, and you start, you trigger neon 22 distillation. And this ultimately leads to the formation of a neon 22 rich shell at some radius outside the center of the white dwarf. And the idea here is that this overdensity that we see later in the crystallization of the white dwarf would be the signature of the formation of this neon 22 rich shell. So forming the shell will release gravitational energy because, of course, again, you're moving neon 22 towards the center, but it releases much less gravitational energy than if you move it all the way to the center. So we're talking about additional delays of the order of 1 gigayear to 2 gigayears, which would roughly match the features that we see here. So before we can test all that more quantitatively and compare to observations, there are still lots of questions to answer. So the first obvious thing is that neon 22 distillation is not yet included self-consistently in white dwarf cooling models. So that's not something that's easy to do, but that's work that has to be done. And the second thing, as you can infer from this plot here, is that everything I've discussed so far is really sensitive to the oxygen abundance that you assume in the core of the white dwarf. And of course, the oxygen to carbon ratio profile in white dwarfs is still very uncertain, mostly because of uncertainties regarding the nuclear reaction rates and convective boundary mixing during the red giant phase. So this problem is really motivating, again, more work to better constrain this oxygen profile. Finally, I just want to say a quick word on the possibility of other distillation processes in crystallizing white dwarfs. So we've looked at the case of oxygen neon cores, where you also have neon 22, but where you also have sodium 23, which is another neutron-rich species. So only neutron-rich species can take place in distillation process. So that's why I'm focusing on those species here. But the upshot of our analysis of this case is that we cannot find any combination of composition in oxygen neon white dwarfs where the condition for distillations are met. So the crystals are simply always heavier than the liquid. So you just cannot trigger distillation. So it looks like this neon-22, this distillation process is really something that happens only for neon-22 in carbon-oxygen white dwarfs. So this result is interesting in the light of recent newly proposed mechanism to create the core collapse of white dwarfs through electron capture at the center of the white dwarf. So this mechanism requires the transport of large quantities of sodium-23 to the center of the white dwarfs. However, gravitational settling has been shown to not be efficient enough to do that. And now we've just shown that distillation cannot do that either. So it looks like there's just simply no way of transporting all the sodium-23 we need to trigger this newly proposed core collapse mechanism. So I will conclude here. So I think neon-22 distillation really can explain both the ultramassive cooling anomaly and also the missing cooling delay for more normal white dwarfs. But of course, there's still a lot of modeling efforts to do before we have a detailed picture and we can really show this clearly and compare with the observation more quantitatively. The other conclusion is that distillation can only take place in carbon-oxygen white dwarfs. And this is interesting, and it leads to another question, which I didn't have time to address, but that is a very important one. What I've explained would imply that those white dwarfs that undergo the cooling anomaly, they have carbon-oxygen cores, but it's not clear yet how you can actually form carbon-oxygen core in ultramassive white dwarfs. So that's another question we will need to answer. So thank you for your attention.
Thank you, Simon. Well, very interesting talk. Really nice to see this cooling anomaly finally getting a solution, hopefully. Do we have any questions? Yeah, Evan Bauer, you can unmute yourself and ask your question.
Thank you. Thanks for a really great talk and all the clarity on the physics that you're bringing into this problem. I find it really convincing and compelling. My question is, because of these sort of bifurcations that white dwarf evolution can experience, depending on sort of small changes in the metallicity, going forward when we're doing kind of construction of synthetic populations, do we always need to try to be very careful to have a range of metallicities if we're trying to account for something like neon-22, because it seems like we need to always be able to produce a small subset that experience a long cooling delay. And in detail, it seems like that's pretty fine-tuned so that we can't just sort of make a population of solar metallicity white dwarfs and have it expect that to work. Does that make sense?
Yeah, I think that's an important, I mean, yeah, this will definitely be something to take into account. And also it will add a lot of, another thing related to that is that when you're in the process of this distillation, the white dwarf stays at an almost constant temperature, but it keeps aging. So it has like a big error bar on the ages for white dwarfs are in the process of doing that. So yes, I think that's really something we need to be careful about when you don't, if you're not sure that your population is really metal poor or really, yes, that's something to keep in mind, definitely.
Thanks.
Maria Camisasa, you're next.
It was really clear how you explained.
I can't hear you.
Can you hear me?
Okay.
Okay, now?
Yeah.
I think you can hear me now. Oh, no. I have this problem with the microphone. Okay, I'll put it in the chat. Because I'll put it in the chat.
Okay. While you're typing, Martin Barson, you can ask your question then.
Hi, Simon. Great talk.
Hi.
It's really nice to hear that stuff and to see a solution coming out of it. I was going to ask a question. If the oxygen fraction is an important parameter in this analysis, could we turn it around and use the luminosity function to determine what the oxygen fraction might be from a statistical perspective across the sample of white dwarfs?
Yeah, I guess, I mean, I would be interested to see someone trying that definitely. I think one complication would be that this oxygen profile will not be the same for any mass. So you expect from just standard single star evolution that, if you have a different mass, the profile will be slightly different. So that's definitely one complication. One other avenue to get more data on this is asteroseismology. So we're starting to be able to probe this kind of thing. So that would be another way. But we need to keep in mind that it's not something fixed. It will depend on whatever happened before to the particular white dwarf we're looking at. So yeah.
Thank you.
Did you type your question, Maria? We still don't see it. There you go. So what is the difference between your phase diagrams and the 3-component phase diagram of Medin and Cumming 2010 presented in figure 4, I think, of Kaplan et al.
Okay, I know.
A very specific question.
Yes. The method we use is completely different, completely independent. I think I won't go into that here, but the physics we put in our calculations is really more detailed, and everything is included compared to what is done in Kaplan et al. 2020. And in particular, they rely on analytic fits to free energy models, and those analytic fits they need to be slightly extrapolated outside their range of applicability in their phase diagram, so that's an issue. But even if we forget about this issue, if you actually compare the two, our results are really similar to the results of Kaplan et al. But we were able to go look at finer details and look at really small neon concentrations, which is what is relevant here to see what happens, because this change in density is really small between the crystal that float in the liquid. So you really need to have all the physics and do this very precisely and accurately.
Okay, we have one last question in the chat by Francisco de Jeronimo. Do you expect that this new mechanism impact in some way the size of the crystallized core of carbon-oxygen ultramassive white dwarfs?
Not sure. The size. So the physical size, because if you change the electron, the number of electron per ion, which you would do by moving those neon 22 around, then I guess you will have a slight change to the size of the crystals. Yeah, I think you will. Yeah, I didn't really think about that, but I do expect a small effect. Yeah.
All right, if there are no more questions, I guess we can move on. Thank you again, Simon.